Whenever you go to your browser, type in a URL and press go, a complex series of orchestrated actions start to happen without your knowledge. These include identifying address of the server, negotiating a connection, and then requesting web pages and accompanying resources from the server. And finally, the server sending you the web page along with the accompanying images, style sheets, scripts, videos, and more. While client and server are the most prominent actors in the story, for this video we are more interested in the process and not the actors themselves. Not who, but how this exchange takes place. This is Ali from Learn Awesome, and in this video we shall explore HTTP, the protocol that makes this magic of web happen. This protocol, HTTP, is part of what is commonly known as layered architecture or protocol stack, where responsibility for actions I just mentioned are performed by dedicated protocols divided into layers, where working of each protocol directly depends on the underlying layer. Though I would try to keep this video independently understandable, I would strongly encourage you to watch a dedicated video for TCP/IP on our channel and in our playlist before or after this one, where we cover most of the underlying layers and especially TCP in detail. HTTP, or most of its currently dominant variants, are built on top of TCP/IP layer. In the layered architecture, each layer has a specific function which it performs and hides its complexity from the next layer. This way, you can write more complex applications without worrying too much about underlying complexity of operations. It's like you don't need to understand inner workings of an automobile engine to drive a car. Some underlying layers of HTTP include the link layer for device to device communication on a local wired network, IP layer to assign and identify computers on the internet via an addressing system, TCP or UDP layers, which are responsible for establishing a reliable or unreliable connection with another machine as you type the URL in browser. There is also an optional TLS or transport layer security layer, which gets into play if you are using HTTPS or HTTP secure, which lets you secure or encrypt HTTP traffic over TCP connection via this additional layer. Currently established HTTP versions are built on top of TCP or Transmission Control Protocol. More specifically, TCP/IP is a transport layer concerned with finding the server, establishing a connection to transmit messages, and error or data loss recovery. So finally, it's time to introduce HTTP. HTTP or Hypertext Transfer Protocol, being an application layer protocol, helps you focus on requesting the actual web page and its contents without being distracted by other stuff. The typical flow of HTTP involves your browser or client making requests for resources like web page, images, style sheets, videos, files, and whatnot via request message, and server responding with a response message. HTTP can also be used to fetch parts of your web page, just something to be aware of at this time. HTTP itself is a huge topic, but we are going to be focused on the message part of HTTP in this video. But before I get into that, let me give you some idea of what is not being covered in this video. HTTP is a stateless protocol, which essentially means each request sent from the client to server is not in context of previous requests. You can think of it as a server having no memory at all. It receives a request, processes it, responds to it, and completely forgets that any of it ever happened. This works for most cases, for example, requesting resources like web pages, where such contextual information is not needed, but not on a shopping website or your social media website where the response must be personalized. For that, there is support for concepts like sessions, cookies, and authentication built in. Though they fall under HTTP domain, they are separate topics and introducing them in detail all at once would be unfair in an introduction video. So these, along with security concerns like CORS or cross-origin resource sharing, caching, client hints, connection management are being deferred to later videos. Also, we are focused on HTTP, but a sister variant called HTTPS or secure HTTP helps make HTTP traffic encrypted and secure. I have it covered extensively in my How Internet is Secured playlist on this channel, so there won't be another video on that, and you are welcome to watch that after this one. But we would be covering some aspects of HTTPS near the end of this video. Now that you are summary introduced to the concepts in HTTP, let's focus on the message part, which are packets of information exchanged between client and server. They are generally categorized into request and response messages. Let's start with request. So an HTTP request is, as the name suggests, a request initiated by your browser to request something from the server. I must clarify here that we avoid using the word browser and try not to do that later. The proper term is user agent, as browser is just one of the many softwares that initiate HTTP requests. Moving on, an HTTP request is a standardized data structure carrying a magnitude of information. A typical request is made of an HTTP version type, a URL, an HTTP method or verb, request headers, and an optional HTTP body. We'll discuss each of these in detail. The HTTP version number is the maximum version number of HTTP protocol the client, or browser, or user agent supports. This upfront notifies the server of capabilities the user agent supports and critically does not support. Server would ideally respond with a response message that is understandable to the client and not something that is supported in higher versions only. In case the server works only on the higher version, the server would send a response with error code 505, which means it does not support the HTTP version of the browser. Right, next up is the URL, and more appropriate term being request target, which generally is the URL of server or web page but can take many forms depending on type of request. Now brace yourself for a whole bunch of unfamiliar terminology, as explaining URL here is a chicken and egg problem, since some of the terms I am about to use would be explained in coming slides. So just bear with me or repeat this part later on. The URL and top part of request, which is more formally called the request line, can be an absolute or full URL or a partial URL, that is, missing the domain name altogether. In the example specified on top of the slide, we are requesting a web page called targetpage.html via something called a GET request. So we specified a partial URL in request line, meaning path to web page from root of the path, or for Windows users, say from C drive but missing the C colon backslash part. In such cases, we specify the domain name in a request header called host, something that I'll cover later. The domain name can optionally be followed by a port number separated by colon sign, but if you don't specify, then HTTP protocol assumes the port 80. Please remember this even if you are unfamiliar with ports, since that is part of core knowledge of HTTP and would come in handy someday. I'll finish by saying that if using an absolute URL in request line, the host header becomes unnecessary, but norm is to build GET request like I am showing in example up top. Just a quick optional FYI that URL in sub GET request can actually contain data sent from browser to server called query string, a term you should be familiar with. This happens with URL followed by a question mark and then key value pair separated by equal to sign, like targetwebsite.com question mark name equal to Ali. That would be all for now on URL. Then is the HTTP method, which is a verb like get, post, put, delete, or a noun like head or options. This is the action request to be performed on the server. Get is generally used to request resources from server like web page, file, CSS, etc. Post is used when sending data from client to server, like creating new user information captured in a sign-up form. Put and patch are used to request updating an existing record, and delete is used to request deletion of some resource from server, like a file or record in database maintained on the server. The two special methods, head and options, have special meanings and are used to check capabilities of web server rather than actually performing an action. Head requests headers that would be returned if request would have been initiated with get request. Say for example, if you are about to request download of a file which can be huge in size, you would first send a head request and response would include the file size. Then you can send the actual request and show a scroll bar to user in the interface with the prefetched information. Similarly, options is used to test if a request would actually go through without any permissions issue on the server. For example, sometimes server only allow requests from specific URLs, and you can use options to check whether a request sent by your user agent would be accepted and processed or simply denied before actually sending the actual request. Headers are a critically important part of an HTTP request. They are key value pairs sent as part of requests separated by a colon sign. They communicate core information to the server about the client, like browser name and version, which in our case is Chrome version 5, accepted language, which indicates preferred language from a server able to provide content in multiple languages, type of encoding accepted, like we are expecting zipped or broadly included or plain text content, and type of requested resource. They can also contain authentication tokens and other data that server might expect. Body is an optional part of an HTTP request. GET requests almost never have a body since they don't require one, while POST or PUT requests almost always have one. They contain data being sent from client to server. For example, if you are submitting a form via POST request, the data would be contained in the body. Response in context of HTTP is something the client receives from server in response to their request sent earlier. That's server's way of talking back to the client. Like request, response is very standardized in HTTP and is made up of following parts: a status line, response headers, and an optional HTTP body. I have provided an example response here, and we'll be discussing each part individually in the coming slides. Starting off with the status line. So status line in HTTP response is made up of several parts that are a protocol version like HTTP 1.1, a status code, which are three-digit codes indicating success or failure of HTTP request. They are important to understand, so I'll be spending some time on this in coming slide. Next up in the status line is a status text, which is a brief informational text description of the status code to make the status code human readable. For example, if your requested web page does not exist, the status line would read like HTTP 1.1 404 not found. If you're a web developer, you would probably need to memorize some important status codes eventually, but to start the journey, you need to know about the categories of status code, signified by their most significant digit. So 1XX is usually informational response status code. For example, 101 means a protocol upgrade, like from going from 1.1 version of HTTP to 2.0 version. 2XX status codes represent successful request completion, like 200, which means request successfully completed. 3XX means redirection. For example, a page that you requested has been moved to another path, so you would instead receive a 301 moved permanently response. 4XX means a client error, like you might be familiar with the dreaded 404, which means the page you requested does not exist. 5XX means something went wrong on the server side, like a crash or any reason which prevented server from performing a successful transaction. Just like HTTP request headers, the response headers convey information about server and its response to the client. For example, the type and language of content via content type header having value of text HTML or application JSON. The content encoding header generally contains the compression algorithm used to compress or encode the response. If you recall, the request headers also had this header which told server which types of encoding can the client process or handle. And the server chooses one of these options to encode the response and notifies back to the client via content encoding header in the response. In case you are not familiar, encoding or compression is a way of minimizing the size of response using a compression algorithm. Like a 1 MB of text can be compressed up to zero point 0.2 MB by broadly, as some experiments suggest. Consider the savings in both data transferred and time, since most of the time waiting to display a page is spent waiting for data to arrive. Transfer of 1 MB file as a zero point 0.2 MB file offers a significant optimization, though there would be some time required to decompress the file on the client side. But that is minuscule compared to network waiting times. Anyway, coming back to response headers, you get the idea how headers are used to convey information between client and servers. Let's move to next object in response. Body is an optional part of response as not all methods expect one. For example, a post request would hardly ever get a response with body. However, a GET request for a web page would almost always get a body containing the web page that was requested. Data contained in body is generally accompanied by content type and content length headers. Now that you understand the requests and responses, you would notice that everything that is happening in your browser is generally using HTTP and its requests and responses. If you go to developer tools of your browser and notice the network tab, you would see HTTP requests being sent and responses being received from the server. Let me show you for a simple web page that we used in an earlier video. So here's a web page from our definited guide to HTML tables, and now I'm going to open Google Developer Tools and go to the network tab, and I'm going to refresh this page and see the request and responses. So if I click on any of these items, let's examine the headers first. So you can see that there's a request URL that is being sent. The request method is GET, since we are requesting a web page. The status code is 200 OK from the server, which essentially means the request was successful. The remote address is the domain name that we are requesting the web page from. And there are a bunch of other headers that we discussed. The content length is the length of the web page in bytes. Content type is text HTML since it was a HTML file. Keep alive, we are going to check later on. In fact, there's another way of looking at the request in the form that is more familiar by now. So if I right click on the web page, go to copy, and let's say I do copy request headers and paste it in Notepad. Here we go, in a form more familiar by now. So a GET request, a partial URL from the root, and specifying that the browser is using HTTP 1.1 and expecting response for that version of HTTP protocol. It accepts text HTML, among others. It The accepted encoding is gzip, which is basically a zip-based compression, broadly, or Z standard, which is an even better compression algorithm. By the way, broadly and Z standard are both much more preferred than gzip, but gzip has been around for decades now, while broadly and Z standard are relatively new. So not all web servers support them. The accept language is in US, which basically means English. There's no cache control, and there are a bunch of other headers which we don't need to get into right now, except this host, which essentially means the domain name followed by the port. Since our web server is running on port 3000 and not the default 80, so we had to explicitly specify it using a colon sign followed by 3000. All right, when we sent this request, what we received was, in fact, let's first examine the response headers, and then we are going to examine the response itself. So I'm going to copy the response headers, go back to Notepad and paste it. So we received a HTTP 1.1 200 OK response, which means server is now communicating using a 1.1 version of HTTP protocol. The content type chosen is text HTML. Content length header value means that the body of this request is of length 2289 bytes, right? And then there are a bunch of other unfamiliar headers that we are not gonna go into details of. So now if we click on the response tab, we can see the actual response or the body of the response, which is the web page that we requested. If you click on any other resource, you are going to find similar things like the CSS file for accompanying this HTML via separate GET request, and we received a CSS file in response. If we go to the headers, you're going to see same kind of HTML headers, request headers as before with some differences. Like if I do this copy request header and go here, there are some slight differences, like we are requesting a CSS file now, and we are accepting a text slash CSS this time compared to text slash HTML earlier. Right? Let's get back to our presentation. Right, we are back. So going forward in our video series, we would be creating a basic HTTP server and see the communication happening, where you would learn how to control, how to handle an incoming HTTP request and respond to it with data and headers of your choice. Another important thing to note is request and response headers are not restricted to ones auto-generated, and you can add your own headers to convey custom information back and forth. A web developer's job requires examining headers and interpreting information for a whole bunch of scenarios, like is the data being served directly from server or coming from a content data network or CDN, which are servers located closer to your geographic location for a faster network response, and intercept your GET request for web page and respond with a static copy instead of actual web server, which might be located somewhere far, far away. To check if site supports CDN and which server processed your request, you use Xcache and server response headers. Caching is a big topic, and every web developer would need to deal with HTTP caching at some point, as almost no modern high volume site works without it. So we shall cover it as well as session cookies and similar topics later on. Being familiar with headers also help you diagnose issues and optimizing your website. For example, you can enhance your UI to show a progress bar as a large content gets downloaded using the content length header for total size and bytes received to indicate percentage downloaded, etc. Let's combine all we know so far and go through a typical HTTP session. There are generally three separate steps involved. First one being establishing a transport layer connection over which HTTP communication must take place. Generally, it is TCP, which we have already covered in dedicated video, but summarizing, HTTP is an application layer protocol which assumes the client has established connection with server before communication via HTTP takes place. Important thing to note here is that HTTP communication takes place over a well-documented default port, which is port 80, or in some cases 8080 or 8000. Though not required, and you can have an HTTP server bound to any port of your choice. If you send an HTTP request to an HTTP server and do not specify an explicit port as URL port, then port 80 would be assumed automatically. I know I'm repeating this part, but this is very important. So coming back to topic, the next steps are easy, that is sending a request and receiving a response. Of these steps, we have covered the request and response parts in detail, but from perspective of evolution of HTTP, the evolution is characterized by the connection part. So you can imagine how important that is, and that is what we shall cover next in detail. Now, one important thing to note is that some concepts regarding connection rely heavily on the TCP layer. So though I'll try to keep it self-contained, it would greatly help if you watch the TCP video in our yet another full stack development course playlist, since it explains how transport layer works in depth and would make it easier to absorb upcoming concepts. Otherwise, you can continue and watch that later and things would make sense. So the HTTP connections are generally one of the following three types: short-lived, persistent connections, and HTTP pipelining. Early versions of HTTP, that is 1.0 or earlier, used to initiate a connection for each HTTP request, also known as short-lived connections. As you would know or would know by watching the TCP video, opening a connection is a big deal in terms of performance, where multiple messages are exchanged between client and server, each inducing network latency and other factors. So it takes a while to establish a connection. Note latency is the amount of time it physically takes for a data packet to go from, say, client to server, and increases with geographical distance. So, quarter to half a second latency is not uncommon. Now, you can imagine that downloading a simple web page involves multiple requests for a web page itself, its style sheet, script files, image files, and other resources. Unless your server is in the same room or the same city, country, or continent, this model is a true performance killer. This was handled in HTTP 1.1 with the persistent connection model, which keeps connections open between successive HTTP requests using a keep alive header, providing immense saving in connection establishment time. Once the connection is set up, you can send a request, wait for response, and then send the next request and so on, while the connection is kept open until the last request is processed or connection times out. Note that 1.1 imposed a restriction that only one request can be processed per connection at any given time. Furthermore, to save servers from being overloaded, and remember, a server is not just serving you, there are thousands or potentially millions of other clients requesting resources from server. A right balance must be struck between maintaining a connection open, which has its own overhead, as well as making sure one client is not being served at expense of others. A default limit was imposed on number of open connections per client. By default, in most browsers, that number is 6. As we have seen many times in videos leading up to this one, batches of 6 connections show up in network tabs of browsers developer tools all the time. And now you know the reason. The world is still mostly on HTTP 1.1, and any HTTP 1.1 server would not let more than 6 requests to be processed. Now, this setting can be changed in browser in advanced settings, but servers also define this limit on their end. So having a situation where you can process more than 6 resources at a time is, well, impractical. Pipeline connections was the next step in evolution where one of the key limitations of persistent connections was fixed. Can you pause and think what it is? Well, the limitation is that any request which takes longer than others would impact all other responses. While it may intuitively make sense as web pages are processed top to bottom, so you would be right in thinking if the top part is being fetched first and later parts later, then it's fine and fair. Well, not all the time. Since most sites have this big high-res banner up top, your entire web page can be held hostage by that banner. So sometimes it makes sense to show the rest of textual website while that image loads. Example aside, the pipeline connection model allows the client to send multiple requests at once to the server as soon as the connection is open. The server would process these requests and send the responses back in full and in the same order. Unfortunately, the last line, that is server responding in full and same order, was a real killer, literally. Though much significant improvement over its predecessors, that is the persistent connection, it just shifted the problem from client to server. Any request taking long time to process by the server blocked the rest. Pipelines really never took off due to this, and other implementation related factors have never been activated by default in any browser and were quickly replaced by a better technique used by HTTP version 2 called multiplexing. Multiplexing, in contrast to pipelining, allows server to break down responses into chunks and send back to client in any order or intermingled order. If you want parallel processing of your request, you would always go for HTTP 2 instead of pipelining. In HTTP v2, both client and server are better utilized, and server breaks down responses into chunks and fully utilizes the open connections and tries to maximize throughput and minimize delay. It also fixes the default limitation of HTTP 1.1 of up to 6 concurrent connections, where one connection was dedicated to one resource being downloaded. So only up to 6 resources being downloaded in parallel. For most cases, HTTP2 would utilize a single connection, but it can increase at its discretion. In the technique of HTTP2 known as multiplexing, the requests and responses are divided into smaller units called frames. frames are interleaved and sent in a non-blocking manner. This does introduce another issue, that is, all requests being processed in parallel can mean no request being handled. Like a web page with 100 images would get all 100 images to be requested by browser in one go, and the entire web page would stop loading as no single image is being fully received and ready to show. To handle this, a concept of stream prioritization was introduced, which allows clients to assign priority levels to different resources, basically constructing a prioritization tree to indicate prioritize this over that. Server would try to fit in responses for higher priority resources first and those of lower priority later. Browsers use these options differently, so with HTTP2, you would feel difference in how a web page loads between Chrome, Safari, and Firefox. Two other related topics are flow control and server push. Flow control is where client or server can enforce limits on how much data is being transferred at any given time, and we stop at that. The really interesting one is server push, which empowers server to send multiple resources back in response to a single client request. For example, if you request a web page which depends on a style sheet, the server would not wait for the client to request the style sheet explicitly. It would send the web page along with the style sheet in response to request for web page only. The server knows best which resources are needed to render the page and can effectively use this technique to minimize network traffic even further. The last great feature of HTTP2 is header compression. A typical header has around 500 to 800 bytes, and headers silently make up a significant portion of overall network traffic on the web. Pre-HTTP2 only allowed the body to be compressed, but headers were transmitted in plain text. HTTP2 allows header compression as well, and I'll avoid the temptation to explain how, as it's not important right now. I had originally planned to keep versioning of HTTP as a separate topic in this video, but there is nothing left to discuss there. So let me introduce the currently final HTTP version, that is HTTP 3 now. Ironically, the HTTP 3 fixes an issue with HTTP 2, which is eerily similar to what HTTP 2 and HTTP 1.1 solved. And if you recall, it fixed the issue of a time-consuming HTTP request blocking other requests. Later versions of HTTP did solve the problem with multiplexing, but the underlying issue of TCP remained. Remember, HTTP is an application layer protocol that runs on top of TCP. Well, the application layer can optimize itself all it can, but in the end, it runs on TCP, which itself has a blocking clause, an issue called head of line blocking. Let me read the relevant line here. If one of the packets is lost en route to the receiver, then all subsequent packets must be held in receiver's TCP buffer until the lost packet is retransmitted and arrives at the receiver. Didn't make much sense, right? No problem, as I'll explain. Messages are broken down by TCP before transmission, and each packet carries a sequence number, so it can be assembled at the receiver side. If receiver receives, say, 1, 3, and 4 packets, but not number 2, it would keep waiting for that packet to be retransmitted by the sender. Now imagine the packet 3 and 4 had a complete response for another HTTP request, independent of the request whose response is blocked due to missing packet 2. But TCP does not know that, and so it won't deliver the full response received to HTTP layer until packet 2 arrives, at which time it would send the two responses to HTTP layer in one go. To fix that, HTTP 3 shifted away from the reliable TCP layer and adopted another transport layer called QUIC or QUIC, which uses an unreliable transport layer under the hood called UDP, which does not guarantee missing packets delivery. QUIC handles that part, but it can also deliver the received responses to HTTP layer as soon as they are available in received packages. Who doesn't like another boost in performance, right? HTTP 3 didn't just stop there. Most sites in the world don't use HTTP, but rather its secure variant called HTTPS or Secure HTTP. Secure HTTP has encrypted traffic which is achieved by client and server negotiating a mutually agreed encryption key to encode their messages. That negotiating part is done after TCP connection is established and before HTTP, and has its own overhead of multiple messages being exchanged to arrive at the encryption key, and is heavier than TCP connection itself. HTTP2 considers this security layer called TLS as optional. HTTP over TLS is called HTTPS or HTTP secure. As per various studies, almost 85 to 90% of web traffic is already on HTTPS and not on HTTP. This means all these websites first establish a TCP connection, followed by a TLS handshake or multiple message exchanges involving latency, and finally are able to start communication on HTTPS via encrypted or secure messages. In light of these findings, HTTP3 simply dumped the optional part as the world has pretty much switched to using a secure communication model already, and the optional part was just slowing things down for most of the users. Think of the extra overhead experienced by 90% of web users each time they establish a connection. So HTTP3 is secure by default and only secure. No unsecure or unencrypted variant exists in the V3 world. HTTP3 in contrast make this layer distinction blurred. The QUIC layer sets up encrypted connections by default at the transport layer, and application layer data is always encrypted. This is done by combining the previously two separate handshakes, that is, the TCP handshake and TLS handshake, into one combined and smaller handshake. Consequently, secure connection setup is fast and there is no concept of unencrypted traffic in HTTP3. There's more to this encryption stuff which is not important right now, so I'll stop here by saying HTTP3 is faster and safer than HTTP2. The client, after establishing an HTTP connection, has an option to upgrade the connection to later HTTP version like HTTP2 or 3. To achieve this, the client can send a GET request to server with an upgrade header listing the HTTP version it wants to upgrade to. If the server accepts the request, it is going to send a response with status code 101 switching protocols. Otherwise, it can send a 200 OK, which essentially means upgrade request was rejected. Note the response is on the current protocol HTTP version. The server would talk the new version after sending this response in current or old HTTP version. Right, finally, this ends our introduction to HTTP protocol. The concepts might look unnecessary, but as you would see in later videos, having good knowledge of these concepts is absolutely critical, especially on a full stack path. I hope you were able to absorb most of these concepts. Please give a thumbs up if you liked the video and consider subscribing to the channel to be notified of upcoming videos like this. Thank you and goodbye.